Tornado season is here. How do we keep our families safe? And what does the current research suggest about tornadoes, how they form, and how we track them? I'm joined tonight by Dr. Jana Lesak Houser, climate scientist and associate professor at Ohio University, to address those questions and more. That's all coming up right here, right now. I'm Sam Chen, and this is Face the Issues. Good evening and welcome to Face the Issues. I'm Sam Chen. Tornado season is here. And we always ask, how do we keep our families safe? What do we do in the event of a tornado? And tornadoes, watches, and warnings fill our region. We'll also wonder, what does the current research say about tornadoes, how we track them, how they form? And what does this research suggest for how we should respond? I'm pleased to be joined tonight by climate scientist Dr. Jana Lesak Houser, Associate Professor of Meteorology at Ohio University. Dr. Houser, thank you so much for joining us.
Thank you so much for having me. It's a pleasure.
That pleasure is all ours. Thank you. Quickly, just a brief background. You serve as Associate Professor of Meteorology at Ohio University. You have your doctorate in meteorology, Associate Professor of Geography, if I'm correct, at Ohio University. You have your doctorate in meteorology from the University of Oklahoma. And you've really committed your life to tracking these storms, studying how they form, and so forth. So thank you for taking the time to be with us. Let me start at the 30,000 foot level. You do a lot of research on what we call extreme weather or extreme climatology. What defines extreme weather and why, for example, things like tornadoes, hurricanes, supercells, what is different between that and a regular thunderstorm?
Sure. So I think you can approach this idea from sort of two different perspectives. You can approach it from a sort of classic scientific perspective, and then you can approach it from more of a human impact perspective. So in the sense of like the definition of severe and what makes severe weather or specifically a severe thunderstorm, there's actually a scientific criteria that is you need to have winds that exceed about 58 miles per hour. And you need to have, or you have a tornado, or you have hail that exceeds about 1 inch in diameter. So that's a very specific definition for what makes a severe thunderstorm. Now, broadening that out to extreme meteorology or extreme weather events, that kind of is more in the context of human impact and basically whether or not there could potentially be or there is impact on human overall well-being. So anything that impacts human lives and impacts perhaps property in a negative way, generally speaking.
I appreciate that breakdown. On the more scientific front, one of the terms that we hear a lot is supercell, like a supercell thunderstorm, but that's not something we necessarily talk about in regular everyday conversation. If I'm at a coffee shop, I'm not talking about last night's supercell, but you do hear from your meteorologist from time to time. What is a supercell? Why should our viewers be concerned about that?
Right. So I'll sort of preface that by saying if you live in the Central Plains, you probably hear this term all the time and are somewhat familiar with it. So there is a little bit of a geographic sort of, familiarity thing going on there. But a supercell fundamentally is a large, violent type of thunderstorm. Specifically, the thing that sets a supercell apart from your average everyday thunderstorm is the fact that a supercell has a rotating updraft that's called a mesocyclone. So as a result of this mesocyclone, this rotating column of air that's being sucked up through the storm, the larger thunderstorm actually is structured differently than your everyday thunderstorm, and it also behaves differently than the everyday thunderstorm does as well.
So when we hear that there's a severe thunderstorm that may lead to high wind and potentially a tornado, are we looking at a supercell?
That is very conditional, not necessarily. Okay. You can get severe thunderstorms to form from everyday thunderstorms, and most commonly the regular everyday thunderstorms will have a potential threat for wind and maybe some smaller hail. But the large tornadoes that you see on TV or that you hear reported on or maybe even impacting your area, most of those will form from supercell thunderstorms.
Sure. Let me ask you about your research. You focus on tornadoes and tornado formation, and your current research is challenging some of the traditional ways that we've always believed that tornadoes were formed, and you're suggesting that they form from the ground up as opposed to in the sky and in the top-down formation. Could you expand on that and give us just a little bit of understanding how you came to that?
Yeah, absolutely. So I have to give a little bit of a history lesson here in order to put this work into context. So tornado research really started getting ramped up back in the 1960s. And in that time era, that was actually about when this bottom-up hypothesis was developed. And that was one of the first hypotheses that was actually employed to explain tornado formation. And then about a decade later, in the 1970s, we started using more sort of computer technology to simulate tornadoes. We started using wind tunnels and actually like laboratory simulations to look at tornado formation as well. And about that time also, we had the advent of Doppler radar. And to clarify Doppler radar, what makes it Doppler is that it actually detects motion toward or away from the radar, not just the presence of something in the atmosphere. So in the 70s, when we were going through all of this new technology, there was a strong both observational and laboratory evidence that tornadoes were actually forming from sort of the middle part of the storm and gradually descending down to the surface. So this was then, confirmed by these new observational radars. So we'll fast forward now, we'll skip for about 30, 40 years here to roughly, maybe 5-10 years ago. So what we have had in the process of those 30, 40 years is we've had a dramatic increase in our computational ability to look at storms, as well as a dramatic increase in our technological advancements for observations. So one thing that we started to notice with some of the newer instrumentation that was coming out is that this signal for strong rotation associated with tornadoes didn't actually seem to be constantly generated at the middle levels of the storm, and yet we were still seeing tornadoes. So this promoted some additional work to be done specifically on looking at rapid evolution of tornadoes and the rotation associated with them. So so there were specific instruments that were designed to look at tornadoes on a very fast time scale. So a traditional radar takes about 5 minutes to scan the atmosphere. Some of these mobile radars that are rapid scan take about 20 seconds. So a very big difference in our time resolution. So what we did is we took these mobile radars, which is basically an instrument mounted on a truck that you drive to the storm, and we looked at storms that were capable of producing tornadoes, and if we were lucky enough, caught a couple in the process. And then looked at the evolution of the rotation associated with the tornadoes. And what we found was not a single case that we looked at actually had rotation that was contributing to the tornado that started at mid-levels of the storm. Instead, what we were seeing was really one of two scenarios. Either there was sort of broad rotation over, the lowest half of the storm that kind of contracted simultaneously, or we had strong rotation that was actually present at the ground level and built its way upward instead of that top down.
Wow. One of the things you talked about was just in the last 34 years, the instrumentation, our ability to study the storms has gotten better. And you're talking about the kind of the stationary programs that I guess National Weather Service uses that it takes about 20 minutes to scan the atmosphere versus what you guys do and go out in a truck and actually chase the storm. It's about 5 minutes on the National Weather Service side and about 20 seconds when you guys are actually actively chasing the storm. What is the difference in technology there, and why is it so much more effective for what you're doing versus what we're getting when we pull up a weather app?
Yeah, sure. That's a great question. It's also a little bit technical, so I'll do my best to keep it sort of on the regular side of things.
Fair enough.
So basically, the Weather Service has these fixed radars that are at a specific location. You can't move them. These radars have been tried and designed to specifically achieve certain observations. So for one, we want to be able to see relatively long distances with these radars. And we want to be able to see a pretty good sample of the atmosphere, a pretty large volume, if you want to think about it that way. So as a result of a couple of factors, but predominantly because of the fact that at the very surface of the Earth, you have things like buildings and trees and telephone poles and so forth. And you can't exactly see and send a radar, like the energy from a radar, through those types of objects. So what we have to actually do is, I'm going to do a little hand display here. So if my hand is the ground, and this is the radar, we actually have to send the beam of the radar up at a slight elevation angle so that it's directed slightly away from the ground. So that creates a challenge when you're looking at tornadoes specifically, because the farther you get away from the radar, the higher the radar's beam is above the ground surface, which implies that you have a vertical gap that you're not actually sampling with these large-scale radars that the Weather Service has. So one of the very fundamental motivating factors to having mobile radars is that you can physically drive your vehicle close to the storm, and as a result of that, you can see much lower in the storm. So therefore, we can get a better idea of what's happening in the lowest couple thousand feet, because most of the time, I mean, unless you're pretty close to the radar within 50 miles or so, most of the time that radar is scanning at heights over 4,000, 5,000 feet above the ground. So that's one component. And then as far as the rapid time updates go, that is expensive, like financially expensive, and it's technically more complex. So there is an active area of research going on right now to try to determine what the best implementation of that type of technology is at a national level, but we just haven't gotten there yet. However, we have the technology, and there's several different types of technology that can actually be used to do this. So we have the technology, and we can therefore use it in a research focused way where we're having, just maybe a couple of these instruments out there instead of the, roughly 60 radars that are scattered through the country.
That makes a lot of sense. Thank you for explaining that. Don't go away. We'll be right back. Welcome back to Face the Issues. Dr. Houser, when we left off, we were talking about your research specifically on studying the formation of tornadoes and how they form. When it comes to predicting and projecting these storms, their path, how does your research contribute to how the public should be acting or reacting or responding to these storms?
Sure. So one of the biggest questions that we have in the science specifically of tornadoes and studying how tornadoes form and why they form is basically, why does one storm produce a tornado when another one that is located maybe just 20, 30, 40 miles away in the same environment not produce a tornado? And we see this happen all the time. So this is something that we're trying to wrap our heads around, because clearly there's a differentiation between these two storms and we can't quite identify what that is. So my work is trying to really sort of put in some of the pieces to complete that puzzle. And we're thinking, if we can have a more full understanding of the actual process involved with forming tornadoes, and if we can for sure identify sort of hopefully some consistency between cases of how this is working, then we can have a better clue to what to look for as far as the processes that are occurring within the storm, or how the storm is potentially interacting with its environment, or how it might even be impacted by non-atmospheric components like things on the ground or on the surface. So that is really where my work sort of fits into the broader picture. And if we can understand why one storm will produce a tornado and another one won't, then obviously we can have a better shot at forecasting and warning for those storms.
Sure. Bring that from the 30,000 foot research level down, through the technical level, down to how this impacts families and communities. What advice do you give families, say, before the storm hits, when the weather is beautiful, before there's any storm on the horizon? What should people be doing in preparation for it? And then when there is a watch and a warning, what should families be doing in preparation for that?
So the most fundamental aspect of preparation is to have a plan in effect, okay? And not just necessarily one plan, but perhaps multiple plans depending on your circumstances. So one of the big conclusions from the work that I've done is that tornadoes form much more rapidly than we thought they did, perhaps, 10, 20 years ago. So our observations suggest that you can go from not having a tornado to having a tornado, basically from the ground all the way up through the middle part of the storm, in timeframes as small as 30 to 60 seconds.
Wow.
So we're talking very rapid processes that are occurring here. So if you are a forecaster or you're working at the National Weather Service and you're trying to issue warnings on these storms, there's actually a lot of really complicating factors that are going to limit those forecasters' ability to correctly warn for those storms all the time. So inherently, what that means is that there's going to be false alarms. So forecasters are going to issue a warning and you don't actually have a tornado happen. Most of the time, that's the issue we're facing these days, rather than the opposite, where you have an event happen and it's not warned on. So thankfully, we're doing well in the sense that we're issuing these warnings, but then they're oftentimes overissued because of the tools that the forecaster has at hand just are not going to ever be able to actually, embody what we're seeing happening physically. So to get back to how people can adjust for this is, most warnings come out with a lead time on the order of 8 to 12 minutes. So that means that the warning is issued, and then 8 to 12 minutes later is when the tornado would actually impact an area. So you don't have a whole lot of time to really think about what am I going to do in the moment in this situation. And that's why it's very important to have a plan in place ahead of time. So depending on where you are you at work? Are you at home? Are you driving in your car somewhere? Are you at the mall? Think about those, the possibility of perhaps a severe weather event coming through, especially if you have heard conversation or your local weather person has suggested that your day might be impacted by severe weather. So when you're at home, the rule of thumb is to go to your basement if you have a basement. In the eastern part of the country, usually most people do have a basement. That gets you in basically the safest place. Now, there's all kinds of myths about like opening the windows and going to the southwest corner and all of this stuff. I mean, that's all mostly mythology.
Okay.
So you definitely do not need to open your windows. In fact, don't spend the time to open your windows. It's not going to matter. Most windows blow out because of debris that hits them, not because of the pressure difference between your house and the ambient surroundings. And also, your house is leaky enough that there's airflow exchange between the house and the environment too. So go to the lowest floor in your house, whether that's a basement. If you don't have a basement, the first story, and you want to be in a room that does not have any windows. So maybe a closet or an interior bathroom. Bathrooms are often a safe place to be, as safe as you can get without being underground. because of the fact that they are anchored to substructure through the piping. So that is a good spot to be. Now, if you live in a mobile home, on the other hand, you should evacuate regardless. There is no safe place in a mobile home. Even though you are out of the elements, your mobile home will blow over and be tossed in wind speeds that are actually even sub-tornado strength. So get out of the mobile home for sure. And in those cases, what you can do is, get in your car and drive the opposite direction that the storm is coming from. Or if you have a neighbor or somebody who lives close by who does have a basement, make arrangements with that person to be able to use their home or their basement or whatever the case is in the case of severe weather. If you are driving in a car, there is sort of differing advice on what to do, but the most sort of current thinking is that you should, if you can see sort of clearer skies, drive to those clearer skies. Cars behave erratically when they're faced with tornado strength winds because of the varying different aerodynamic properties of them. So if your car is facing into the wind, it might do one thing. If it's facing across the wind, so it's hitting the wind's hitting the side of your car, it could do something else. It could flip it, it could lift it up. It's very sort of chaotic, the behavior. So if you can safely drive away from a storm and you're in a vehicle, that is recommended. Now, if the tornado is basically like right on top of you, this is where things get a little hairy. Some people will say, leave your car and go to a ditch. Other people will say, stay in your car because you're offered better protection. The consensus there is like, if a tornado is really basically like on top of your vehicle, probably the safest thing to do is actually to stay in your vehicle and to kind of crouch down so that you get your head below the window level. In most tornadoes that are, not the super duper gonna loft your car, 25 feet in the air, most vehicles, you will be relatively safe in that situation. But even if you get rolled a little bit, nothing different really than a car accident. And that puts you in a little bit of a safer position than if your body is just physically out there.
That's a great point. Well, thank you for that advice. Again, we'll be right back. Welcome back to Face the Issues. Dr. Houser, thank you for being with us. Thank you for your research and for really just helping us understand these storms. Our last segment, we always like to get to know our guests a little bit better. Storm chasing, what you do is, you're actually out there in the fields, in addition to teaching in the university classroom. This is something that's fascinating. We usually see it in movies. What got you interested in it, and what got you to where you are today?
We joke in the field of meteorology broadly that it's like a genetic mutation because this is something that I have had an interest in since I was in second grade. I remember my second grade elementary school teacher, Mrs. Rader was her name, West Coastville Elementary School, for those
I remember her.
Yeah. We did a weather unit in science, and I just really thought it was fascinating. So from there, I started watching the Weather Channel, back in the day before the Weather Channel was kind of quirky and networky and a little bit more sciencey. Sorry, Weather Channel. But anyway, and I found tornadoes particularly fascinating. And I think part of it is there's sort of this dichotomy that goes on. There's this like graceful beauty when you're watching a tornado, and yet it is wreaking havoc on things at the ground. So I was just really captivated by that at a very young age. So I kind of went through my school years knowing that I would probably pursue this, and ended high school with a couple of potential ideas for majors, but really knowing how intensive the math and the science are for this major, I wanted to go right into that without having a break, because I think that would be a lot harder to go back to 10, 15 years after the fact. So I majored in meteorology in college, went to Penn State University. And then from there, I had a couple of great experiences, including some opportunities to go into the field and to chase tornadoes as a junior and as a senior. And I just knew that that's what I wanted to do, and that was, kind of a lifetime dream accomplished. So I went into graduate school. I also knew that I really enjoyed education, and I like connecting with students, and I like the interaction between students and me, and they get me to think about problems differently than I do on my own. So I thought that a career in academia where I could do both research and teach would be a good fit for me.
Yeah. In the last 30 seconds or so, what advice do you have for a young person who sees this and says, "Oh, I want to do that"? What advice would you give them?
Well, I say pursue your dreams, but know that it is also a hard road. There are many people that enter the waters and considerably fewer that come out. But investigate your options and start thinking about things early on. There's great resources out there now with the internet that can tell you about classes to take, that can tell you about jobs and career paths, and really, investigate your opportunities. Storm chasing by itself is generally not a career for most people, so there's usually some kind of other component to that. But, there are a few people that can make their income and their livelihood through storm chasing.
That's great. Dr. Houser, thank you for joining us. Stay safe out there. And that is all the time we have tonight. Thank you so much for tuning in, and join us again next week as we unpack another issue. My name is Sam Chen. On behalf of all of us here at Face the Issues, thank you and good night.